We will move on to the next algorithm, which is hash join. This is a very, very important algorithm and a little more complicated than the previous ones. Once more, this is applicable only when the condition is equality, that is, it is an equality join. So, the idea is the following, is that take a record TR and take a record TS. Since it is an equality join, they must be equal. That means they must hash to the same position. So, if this is a hashing function that is applied, they must be hashed to the same position. So, what is being done is the following, is that first of all, both the relations R and S are hashed to the same hash table, and then from each of these hash buckets the matching records are picked up one after another. So, that is the entire algorithm, and there is a hash function to partition the records. So, if the hash function, if the relation does not fit into memory, then this hash function needs to partition it, and then it is called a partition hash join. And just a little bit more detail on that algorithm, what it being done is that, so suppose the hash table entries are from 0 to n minus 1, so there are n entries. So, each record, also each record of R and S, so say this is HRI and HSI, these are the partitions of R and S. So, this means that essentially hash function on TR is I, then it goes to the partition HRI, and hash function of TS is I, then it goes to the hash function of the hash bucket of HSI. Once that is done, the partition HSI is read. So, these are partitions. Once this step is done, this partition HSI, one of the partitions from HSI is read. So, this is read into memory, this is read into memory, and in memory hash index is built. So, remember that this partition hash function is the out of disk. So, this is operating at a disk level. So, this is partitioning the tuples into a disk based partition. So, each partition is in separate position in the disk. Once that is being read, and in memory hash is built for this partition only, each memory hash for HSI only. So, all the tuples in HSI, there is an in memory hash function that is built, and then what happens is that for every record TRI, which is in this hash partition HRI, so this is called the probe. So, this is probe to find out the corresponding matching tuple. So, this is a build because an in memory hash is built and TRI is probe. So, that is why there are some nomenclatures that are used. So, S is called the build input. The reason is S is used to build an in memory hash function, while R is called the probe input. The reason is tuples from R are used to probe this in memory hash function that is built for the other relation. So, this we should remember. Okay. So, couple of things is that each of the partition of the build relation must be in memory, otherwise this whole procedure does not make any sense, and therefore, the build relation should be smaller. So, the build relation should be the one that is the smaller one. So, if between R and S is smaller, S should be the build relation. Now, let us analyze the sizes of this. So, suppose there are n partitions. Now, each partition must fit into memory. Partition must fit into memory. This is the one invariant that we require. Suppose the number of blocks in a memory, this is the memory size in number of blocks. Fine. And suppose the build relation has got BS blocks for the build relation. Okay. Now, what do we want is that this n should be greater than equal to BS by M. Why is this required? Because the total number of build relations is M, and if each of them fits in M, that gives you the number that many partitions can be handled, and n should be more than that. So, that means if n is more than that, if the actual number of partitions is more than that, then each partition, the size of each partition will be less than what can be fit. So the other condition of course is that M should be greater than N, because each partition must fit. So everything inside the partition must be fitting in the memory, and the number of memory sizes. So from each partition a block must be read. So the one block from every partition can be read. So that is M should be greater than N. Now combining these two, what we can then get is that M is greater than equal to Bs by M. So this is what the condition you are getting, or we can write it as M should be greater than equal to square root of Bs. Now this is one thing that must happen. So the memory size must be greater than the square root of the size of the build relation. Now if this happens, then a single partition is good enough. If this however doesn't happen, then the strategy called recursive partitioning needs to be employed. The recursive partitioning, the intuition of the recursive partitioning is the same as the merge sort, the external merge sort that we saw, is that if things cannot be done in the one pass, then whatever can be done in the one pass is done, then things are delegated to the next pass. So the same thing, if this is not done, so initially what will happen is NS is chosen such that this is less than or equal to M, and then each partition partitions are built first. So partitioning is done at the first level, and then each of these partitioning is then again, but now each of these partitions cannot fit into memory, so each of these partition is then again repartitioned, and this goes on till finally one of the partitions, till finally the partitions can fit into memory. So this goes on till it fits into memory. That is what the recursive partitioning does. So this is the important thing, that it must fit into memory. And there is a hybrid hash join which just retains the first partition always, so that is fine. Now the important thing is to analyze the cost of this hash join strategy, or it may be recursive partitioning, etc., etc. So relation R contains BI blocks. So initially it requires BI transfers to read relation R. Fine. Now the total number of blocks after the partitioning, so this is trying to partition relation I, trying to partition relation I. So this is what the operation that we are doing. So BI transfers read for reading. Now this may, what may happen is that after the partitioning is done, it may produce BI plus N blocks, because each of these is just one extra tuple is there, so which doesn't fit into the block, etc. So there can be BI plus N. So what may happen is that, so this needs to be written back, and then needs to be read, written back, and then read again, because each partition is then going to be read. So this uses 2 BI plus N, and then there is this BI. So if we add these two numbers up, for each partition this is 3 BI plus 2 N, that is the number of transfers. This we are only worried about transfers now. So this is for each relation I. So the total number of transfers therefore is 3 BR plus BS plus 4 N. This is the total number of transfer that is required for the initial phase, or just the required for the just the initial phase. Okay, fine. So what are the number of 6? If we go ahead using the same thing, the number of 6 for reading this, making the partition is that, again suppose BB blocks fit into memory, so BB blocks, so memory size is in BB blocks, BB blocks from each relation fits into memory. So then there are BI by BB 6 that are required to read all of them. Then similarly BI, so this is for reading, and then BI plus N by BB 6 for writing, plus that same kind of thing. So then reading the N partitions require, reading N partitions require N6, because each partition is in a separate thing. Reading N partitions that requires N6, So the total number of 6 that is required is your BR plus BS plus N, I mean of course twice of that, by PB. This is these two terms plus of course this N, so plus 2N. This is the total number of 6 that is required for doing this hash join. Now this is of course assuming that there is no recursive partitioning, because once you read and then reading these end partitions is good enough to do the hash join. One important thing also that I must highlight here is that the output cost is not taken into care of. So it will require some cost to flush the output to the disk, to write down the output to the disk, but that is not taken care of. Generally output is just assumed to be given back to the user in the console or some other manner. Coming back to the cost of a hash join, the previous case was assuming there is no recursive partitioning. If however recursive partitioning is required, then the situation is a little bit different, and we can analyze it in the following manner. So the number of passes, the first thing to enter is the number of passes that is required. That is the first important thing, is log m times bi, right? Because that's the m is the memory size, so that many passes are required. Now for simplification, if we ignore half field partitions, the total number of transfers therefore is, this has to be multiplied, because in every of these pass the entire relation is read, etc. So this is of course, and there is a similar term for S, and plus your BR plus BS. This is for finally reading the two partitions, all the things. So that is the total number of, this is for transfers, this is the total number of transfers that is required, and the total number of 6 that is required will be, instead of BR, this will be BR by BB, that many 6 are required, and then it's the same formula otherwise. So plus 2 BR. Once more I want to highlight that I am ignoring the half field partitions. I am assuming there are no half field partitions, all partitions are nicely behaving. This of course will not happen, so plus n etc. par of these things needs to be added. So this plus 2n. So that many 6 is required. So this is for recursive partitioning, because this is the number of passes that is required for relation. So for partitioning relation I, but it cannot be done in one pass. That is the whole point. So there is a extra cost that goes into each of these factors. So this is the number of passes, the cost. So for each of these passes everything is read and written. So that's the idea of recursive partitioning. So let us take a stock of what we have done so far. So we have handled selection, we have handled sorting, and we have handled join. So these are the 3 main operations that we have handled so far. There are some other kind of operations. First operation is a complex join. So it's, what is a complex join? I mean it is not so the join condition is a disjunction or conjunction, etc. So disjunction or a conjunction. It's not a very simple one attribute to another attribute join. So there is a little more complicated predicate. The predicate is a little more complex. Now of course the block nested loop join can be applied, because the block nested loop join doesn't depend on what the predicate is, it just takes up 2 tuples and applies the join condition. So this can be always done. If the disjunction and the conjunction is only based on equality, then this hash join or merge join may be done depending on the equality, and then those indexes, the union and intersection needs to be done. So depending on whether it's disjunction or conjunction, union and intersection can be done on top of your merge join or hash join. So that can be handled. Okay. So this is for the complex join. There is one another important operation that the database needs to do sometimes. It's called the duplicate elimination. If you remember, SQL by default is a multi-set, whereas relational algebra is set, and there is a way of asking the SQL to produce a set by specifying the keyword distinct. Now when that is being done, what it essentially tries to do is it finds out the duplicates and eliminates them. So how is this duplicate elimination done? Well, the first thing that comes to mind is hashing. Of course, hashing can be done. So all the tuples can be hashed to find out, and then whenever the two tuples hash to the same location, they can be checked attribute by attribute to say if they are done. The other a little non-standard way of doing it is sort it and then go over the sorted manner. So each tuple is compared with only the next tuple. So these are the two ways of doing the duplicate elimination. So the analysis of duplicate elimination is the same as doing the hashing or the sorting. So that's the same thing. Then there are certain set operations that the relational algebra and SQL needs to handle. So what are the different set operations that can be done? Union, intersection, difference, all those things. Now if the relations are sorted already, then this is easier, because then it just needs to be scanned, the two relations or the two sets, etc. just needs to be scanned in order, and this can be applied. The other way of doing it is that an index can be built on one of the sets, index on one set, and the other can be then tested on the other set. So you see that these set operations, etc. is kind of like the join, and the idea is instead of two relations there are two sets, but then the intersection union operations are being done in that almost the same philosophy, using the same philosophy. So all of those things can be done. The next important operation is aggregation. Now aggregation can be done with or without grouping. So if it is without grouping, then it is easier, because then you just need to go over all the tuples and just find the aggregation function. So what is more interesting is aggregation with grouping. So the important part is how to do the grouping. Then of course the first and the most basic idea is to use the hashing for each group, and then for each group essentially becomes an entity becomes a relation by itself. I mean, it can be treated like a relation by itself, and then it can be aggregated. So that's the aggregation with grouping. The hashing is required to partition the relation into this group. A very important that we have left out is the outer join. So whatever we have been talking about so far is on the inner join. So we have been assuming that the operations are inner join. So now outer join, to recall, even if a TR and TS do not agree on the equality, suppose it's a left outer join, then the TR must be output as well. So that's the whole use of outer join. So how to handle that? So once more, the block nested loop join requires no modification, because this is the most generic algorithm, and if the TR and TS match, it is outputted, otherwise it is padded with suitable null values, etc. can be done. Fine. For the merge join, what can be done is that suppose it is a left outer join, then when R is being scanned, even if there is a matching tuple in S, fine, this is output. If there is no matching tuple, even then this is output. So when R is being scanned, it is made sure that everything on the R side is being output. So the merge join can also be handled. The question then is, if it is a left join, suppose it is a left join, the question is which one should be the build relation and which one should be the probe relation for the hash join. So suppose it is a hash join. So hash join can work in the same manner. Suppose it is the left thing, and one of these R can be used as a probe relation, or the S can be used as a probe relation. So the question is which one should be used as the probe relation. If it is a left outer join, then R should be the one which should be used as the probe relation. The reason is S can be used for build, and every tuple from R is probed. If it is matches, then that is output. Even if it is doesn't match, then the R side is fine and the R side is simply output. This is all fine for the left outer join, and similarly the strategy can be used for right outer join. However, what happens when the operation is a full outer join? So for full outer join, of course the merge join can be used easily because everything is output. For the hash join, it's a little bit more complicated, and you see that this probe and build relation is not completely useful because suppose there is an S that is skipped on. How do we know that S has been output or not? So generally the hash join algorithm is not used for the full join. However, what can be done is the following, is that for every relation in S, for every tuple in S, there is a marker. So if S is probed, one of the tuples in R probes it, then this is marked as 1, and by default it is otherwise 0. At the end of the whole output, a pass is taken over this S, and everything that is 0 is output. Why is this? Because if it is 0, meaning nobody from R has caught it, and R is suppose the left outer join is done in the left outer join manner, so everything from R is actually handled. So but this S needs to be also handled, so this is output again. But you see that this is a little bit more clumsy and not very efficient algorithm. So this is generally avoided, and simply a merge join or a block nested loop join is actually the one that is preferred by all of these things, because it is the most generic. And if the outer join contains conjunction, disjunction, etc., then you can see how complicated the algorithm can become. So this finishes the module on query processing, and we have seen how the different query algorithms can be handled, etc. Next we will start on the query optimization.